Welcome back everyone to the GOCC. Today we have Carrie Frizzell who's going to talk about the tree growing sequence.
Thank you, Alex, for inviting me, and also Galen for co-organizing with him. And thank you everyone who's attending. So this is my obligatory title page, I guess. So I'm just going to go ahead and start with sort of the origins of this talk and the problem that I'm thinking about. And this is based on a paper that I put on the archive not too long ago. Although the version that's up there, it still has many typos, so it'll probably be replaced with corrections soon. But this K6 diagram of objects, in some ways it's wishful thinking, because what these arrows are representing are bijections between each pair of objects. And some of these bijections do exist in the literature, but there are some of them which are not necessarily direct bijections. For example, I don't think I've never seen a map described that goes directly from critical configurations to tiles of some zonotope. So in a way, this diagram is wishful thinking, but some of these bijections do exist. And what I'm focusing on in this talk is this K3 that I've bolded in blue. So bijections between G parking functions, spanning trees of that same graph G, and then monomials of the Tut polynomial of the graph. Now, there is a way I might get a chance to talk about it at the end, depending on time, but in this side, and maybe technically it's better if I kind of put isomorphism there instead of equal. That might be better for some people, but there's a way to fit some stuff about tropical curves, aka metric graphs, in the diagram, but for now I'm just focusing on finite graphs. So there's a lot of previous work found in the literature on this triangle diagram. So I've just listed some people who have been involved with these bijections, and there are many more than what I've listed, but all the ones that are listed on this page are ones that I've sort of had read and gotten most of my background information from. So I won't stay on here too long. So let's talk about some basics, some definitions, notation, and then some reminders, because some of you might know a lot about what I'm talking about already, but we're going to be working with multigraphs. And if you do have any multiple edges between vertices, then you can just order those edges internally between those two vertices. Just put some order on them. And then we also want to have a root vertex, and we'll be calling that Q throughout the talk. And then a spanning tree is a connected spanning subgraph that has one less edge than the number of vertices. And for every spanning tree that we have, we're going to direct edges toward the root.
Sorry, what do you mean by order internally?
So order internally, by that I just mean, let's say you have three edges between these two vertices, then you'd want to call them like E1, E2, E3, just so there's some preference between those multiple edges.
I see.
Yeah. All right, so let's start with the Tut polynomial. So I've written down 3 formulations of the Tut polynomial for a graph. And this first formulation, let me explain. So this notation just means the set of spanning trees of G. And this formulation of the Tut polynomial is based on the notions of internal and external activities of your spanning tree. And I'm going to get back to this later, so I'm not going to explain it into detail, but internal and external activities are based on some ordering of the edges of your graph. And so for each spanning tree you look, you can count these activities. And this is actually what Tutt had in mind when he first defined the Tutt polynomial. He used notions of activities, and his goal was to find a generalization of the chromatic polynomial. So this is pretty similar to what Tutt first had in mind. So the second formulation is as a sum over spanning subgraphs of G. So you can think of it as being as a sum over edge sets, but if your edges do not, or if you have any isolated vertices, you still include those isolated vertices in your spanning subgraphs, or in your subgraph, so that ends up being spanning. And then C of G, this is just the number of connected components. Same with C of A, so number of connected components. So this is another formulation. And then this third formulation, this is the recursion formula, and I usually refer to it as the deletion contraction principle. So what it tells us is that if you can compute the Tutt polynomial of a graph by performing a sequence of edge deletions and edge contractions. So we have special cases. So if you choose an edge E and it happens to be a loop in your graph, then the recursion looks like this. You delete E, you delete the loop, and then you multiply everything by Y. If E is a bridge, you end up contracting E and multiplying everything by X, and then otherwise you just add the polynomials for the graph with E deleted and the graph with E contracted. Okay, so I'll move on. So that's the Tutt polynomial.
Can you remind me what a bridge is?
So a bridge would be like an edge cut set of size 1. So if you remove this edge, it will disconnect. Well, I guess it will increase the number of connected components by 1 if you remove that edge. So that's what it means to be a bridge. So remove it, increase the number of connected components. So in particular, just what I want to point out, because it's relevant for when we think about bijections, this first formulation is a sum over the set of spanning trees of G. So the number of monomials in the Tutt polynomial is going to be the number of spanning trees. Or in other words, if you evaluate this polynomial at x equals 1, y equals 1, then you get the number of spanning trees. All right, so now I should clear. Now let's move on to G parking functions. So first, we need to define what the out degree with respect to a vertex subset means. So all this means is if you have, let's say this is a subset of your vertices, and here's some vertex V, then V might be connected to, it might have neighbors that are inside of A, but the out degree with respect to A is just going to be the number of edges which connect V to a vertex outside of A. And that's including, yeah, with multiplicity. So you just count, the out degree here would be 4. And that definition is needed in order to understand what is meant by a G parking function. So a G parking function It's an integer valued function, well, positive, non-negative integer valued function on your vertex set. And I take out the root vertex q. You can give q a value if you want, but I usually just take it away. And it's this type of function such that if you look at any subset of the vertices, excluding q, you're going to find some vertex that has the out degree greater than the value of the function at your vertex. And we already know that it's greater than or equal to 0 based on the codomain of the functions, of the function. So one thing to note is that we actually obtain the classical parking functions with the complete graphs. So that's sort of the connection to, or why they're called G-parking functions. And in other contexts, these are what are called Q-reduced divisors. So in particular, if you are familiar with some combinatorial algebraic geometry, usually the word like a Q-reduced divisor is used. And so that's why I wanted to call my root Q, because of these being the same as Q-reduced divisors. So G-parking function, the definition of a G-parking function can also be stated pretty nicely in terms of chip firing games. So I'll just draw an example in case you're not familiar. So let's say we have this graph and maybe I'll add a few edges, more edges to it. So let's say we have this graph and let's say we have 2 vertices here and I have 1 vertex here. So I always like to think of it as you can fire 1 vertex at a time, but I always like to keep the thought in mind of firing multiple vertices at a time, because we're thinking about subsets of the vertices, which can definitely contain more than 1 vertex if your graph does. So if I want to fire this subset of the vertices, then I simply send a value, or aka a chip, to every edge going from a vertex in this set to a vertex outside of the set. And then you reduce, and then you change the values accordingly. So this would be changed to 1, 1, so actually 2, 2, and then -2. So the way you formulate the definition of a G-parking function in terms of chip firing games is that it's going to be a function on your vertices with non-negative integer values, such that you cannot, no matter how you choose to fire, you're always going to get negative values. So that's just one other formulation, but I'm not going to focus on the chip firing formulation. Although I think, I think it's sort of maybe the easiest way to think about these.
I think that's the same as a super stable configuration, right? That's what I've also heard.
Yeah, that's how I used to describe it last summer. Some of my students, I kind of gave them a special topics lecture on chip firing, but they didn't know, they didn't have very much background. They just had learned intro graph theory. So I used super stable configurations. Yeah, that language. All right. So now I want to sort of talk about where, because I'm going to soon define a tree growing sequence. So I want to talk about some thoughts that I was, maybe not me personally, because a lot of this I've talked with my advisor about these bijections. I've talked with a lot of other people about them. But these are just some comments and maybe some things to think about. So these bijections that we have between these 3 objects, so I'm having some trouble with this. So we have this triangle, we have spanning trees. I'm going to call M sub g, this is the monomials of tut. And then the g parking functions I'll denote in this manner. And then q, just to specify that our root is q. So some things we can think about is the dependence of these bijections on certain choices. So certain choices could be, well, for one, the choice of root vertex. Some algorithms depend on a vertex order. Some algorithms depend on an edge order. Maybe there are other dependencies. And what we might think about are, well, is there any compatibility between these choices? So for example, let's say we have an algorithm that takes a parking function to a spanning tree, and it depends on a choice of vertex order. And then we have another algorithm which takes a parking function to a monomial of tut, and it depends on something else. And then we also have a choice for this arrow. Is there a way that these choices are compatible so that we can get this thing to commute? Okay, so that's one thing that we might think about. Another thing is, this third bullet point kind of has to do with sort of what spurred this work is, does every bijection that goes, so I should have been more specific. So does every bijection between G parking functions and monomials of the tut polynomial have to go through spanning trees? And in that, do we always have a way to automatically associate a spanning tree given a map between G parking functions and monomials? So that's something I'll talk more about later if it's not so clear what I mean by that. So what I was thinking about is I was thinking about this compatibility between choices. So or rather, I was thinking about the compatibility between choices and what other types of choices you could make when you are constructing these algorithms which give you these bijections. So one thing that I had thought about is if you sort of have a mix between an order on your edges and as well as a preference for growing a certain subgraph in your graph. So I'll just draw a picture. I don't want to talk about this in too much detail because I didn't pursue it very far before I started thinking, before I got to the thing in the next slide, I guess. So for example, maybe you have an algorithm where you are going to construct a map between your parking functions and your spanning trees. And maybe you have like a DAR-like burning algorithm, but you sort of want to make some modifications. So what I've done is this subgraph that I've scribbled out, maybe I want that to be my preferred subgraph. So perhaps ideally I'm going to try to obtain this subgraph before I pick up any other edges. And then if that happens, then I put an ordering on the other edges, and this ordering, after I grow this subgraph, it will tell me now which edges, in what order I want to try to grow these other edges. So maybe that's not too illustrative, but that's just sort of what I had been thinking about. Have some preferred subgraph you want to obtain, and then have an order on the edges that aren't in that preferred subgraph. Okay. So, so I guess some other things I had in, well, I'll talk about them after the next definition. So overall, the goal was to, in thinking about these bijective correspondences between these three sets of objects related to a graph, is there some way to generalize these bijections which will make these choices kind of make sense or kind of make them fit together? So this is where the definition of a tree growing sequence comes in. So I can't claim that this definition is anything magical because I don't think it is. And I believe there are a lot of things that are similar to a tree growing sequence. But let's go ahead and define this. So I'm thinking for now only about connected graphs. And I guess I should put connected multi-graphs. So we're given a connected graph and the set S of all edge subsets which contain Q as a vertex. So I didn't originally have this. I didn't have this in my original definition. I just had, okay, let's just think of all edge subsets, which we could still get rid of the condition that Q is a vertex of at least one of the edges in the edge subsets, but I decided to keep it in there for some purposes. So a tree growing sequence, it's a collection of tuples where your tuples are a subset of edges S, and then a function on the set of rooted subtrees of S. So this is some abuse in terminology because technically I should say that an element of H sub S is a collection of edges where the subgraph on those edges is a rooted subtree, but I think that's a little too much for me to write down. And what has to be true is that if you take such a tree in H sub S, then if you apply your function to T, then you can't get an edge that's already in T. And then it has to be true that if you add the image of T to T, it's connected. So I guess I already wrote that. I don't need to rewrite it. You get something that's connected. So in other words, a tree growing sequence is really just a collection of like mapping data. And that's one way to think about it. Data that's telling you if you have a certain tree, which edge do you add next? And just like I could get rid of this condition of containing Q as a vertex to make something more general, I could also change rooted subtrees to just subtrees or just subgraphs of S or edge subsets of S. So that's always a possibility.
So the subtrees don't have to be spanning, right?
No, they don't. Yeah, just any subtree rooted at Q. I'll draw an example of like, so yeah, question, what if E of T equals E of S already? So in that case, you that means you don't have, it's not defined. It means the function's not defined on, so.
So S is not in sigma then.
What?
So S is not in sigma then.
What was that? I'm not sure what.
Sorry, in that case, there is no pair in sigma that has S as the first entry, right?
Oh, if E of T equals E
Yes.
of S. Well, it's still, we still can have S like as a, it just means that this is not defined. Because there's no other edge to grow.
I'm a little confused about the definition. So we have a set of subsets of edges, edge set.
Yeah.
But Q is a vertex.
Yeah. So that's where the language is a little confusing. So it's just like if these are edges in your graph, then just one of them has to have Q.
Okay.
Yeah.
Thanks.
Yeah. That's why I debated like leaving this condition out, because in a lot of ways it's not necessary, because you can always just afterwards say that you only want to take the subsets which have Q as a vertex when you're considering a certain tree growing sequence. I think if I write down an example of like what this data looks like, it will be clear, more clear.
We do also have another question in the chat, which is, what is T?
So here, well, T, if T is the argument of this function, it means T has to be a collection of edges inside of S that form a rooted subtree. So T. So I'm not sure. I see like the questions popping up, but I don't have an easy time.
Yeah,
getting to
just
it.
the person who asked the question just said thanks. So
Oh, okay. Yeah, you're welcome.
Yeah. I'll keep an eye on the chat and let you know when there's questions.
Okay.
It is really hard to do while you're giving a presentation because the screen sharing's not there. So
Yeah. All right. So I want to go to the next slide, which is a blank slide, because I'm going to write down an example of this data. So maybe you get the sense that this is a lot of data, and it is a lot of data. So I'm going to have to write it down for a very small graph. And for some reason, oh, it's because I have my eraser. So let's just look at K3. So I'm going to let this be Q, and I'm just going to name my other two vertices, because then the data will make more sense. So if I write, so here, if I write the edge subsets I want to consider, and then I'm going to sort of draw diagrammatically what sigma sub S could look like. So we certainly have the graph itself. We have these two spanning trees. Sorry, all three spanning, and then that spanning tree. And then we have some single edges. And then the third edge, since it doesn't have Q as a vertex, we are technically not considering it in this set of data. And then diagrammatically, sigma sub S could look like the following. So one thing, and I forgot to include it in the definition. So I want to technically include Q. So yeah, sorry, I didn't include this as a technicality. I always want to consider just the vertex Q itself as part of these edge subsets, which sounds kind of strange, but I apologize for not mentioning that technicality. But for example, for this first tuple, maybe our map, our map sigma sub S looks like this. Maybe it tells us first to add this edge, and then to add this edge, and then to add the remaining edge. So here, like, this is not itself a tree, but it's still an edge subset of G. So it's okay to attain it, but then we know that sigma sub S can't be defined on this. And then sort of similarly here, well, maybe here we want to first grow or add, I'll say add, and then say grow, maybe first add that edge, and then add that edge, and then that's all we can do. And then you can sort of imagine it for those other subgraphs. So one thing with this definition is you don't necessarily have to have any compatibility with these sigma sub S's. So what's a good way? it might be a little bit hard to see it on this graph. Maybe these first two graphs are enough. So for example, here I'm first adding this edge, whereas here when I start with just my vertex Q, I actually add this edge. So even though this is a subgraph of my original graph, we don't have to add edges in the same order.
Like we actually can't see what you're pointing to now. Are you saying that like?
So like there's like, even though this is a subgraph of our original K3.
Oh, the circled thing?
Yeah, the circled thing.
Okay, so I wasn't sure what you were referring to when you said this, because I think I was like,
oh,
for the
yeah, I
point
tried to circle it, it didn't show up.
Yeah.
So although this is a subgraph, yeah, this spanning tree is a subgraph of G. We're not adding the edges they have in common in the same way, in the same order. And that's not something that's not required for this general definition.
Can I ask sort of a clarifying question?
Yeah.
Could you say that this tree growing sequence is basically, it's a way of starting with a root and ending with a rooted tree, where at each step of the process, you look at what you've currently considered as part of the tree, and you look at like the sigma of that, like so far what I have, and that determines what edge you add next. Is that the idea behind what this tree growing sequence is?
Yeah, just like the very simple, like one maybe first thing you might learn in an intro graph theory course about growing a tree. You just want to make sure that you're maintaining a connected graph at each step, and you want a tree, so you only add each vertex one time. Actually, let me go back to this page. I will uncover it in a second. Now that, yeah, so I actually don't want this. I must have copied this from an old version. No, actually, sorry, that's okay. I must have copied this from an old version of my draft. But I actually do want to just change this to rooted subgraph. So we don't necessarily need we also might have it on, so let me draw a different example. Because I do want it to be a little bit more general, but yes, we're using it to grow a tree, but a priori, we can also technically have cycles, but the algorithm which we apply doesn't allow that to happen. So instead of our domain being rooted subtrees of our edge set, I'm going to allow any rooted subgraph of our edge subset. So it's very possible, like if I have K4 and this is Q, if I'm just considering the entire graph itself as my S, then it's very possible that sigma sub S will tell us to grow a cycle. So that's possible, but it's the way in which we apply the algorithm that I'll explain shortly that won't allow us to have cycles and hence grow a tree. So I think my computer maybe there. Okay, so here's where we're going to define an algorithm based on a given tree growing sequence. So it's pretty simple to define an algorithm because you just want to make sure that you end up growing a tree, which means you do want to maintain a connected, cycle-free subgraph at every step until you've collected all of the vertices in your graph. So maybe you can think of ways to do that. If you're just given a tree growing sequence and nothing else, you can just say, oh, if we're told to grow a cycle, throw away that edge. So for us, we're going to start with another piece of information. And in this case, we're going to start with an integer valued function on the vertices, excluding q. And then we can tailor the algorithm so that we only grow edges to vertices we haven't already collected, so that we ensure that we won't have any cycles. And what the goal is when we take a function, and in particular, if we take a G parking function, we want to be able to produce a spanning tree and a monomial of the Tut polynomial when we apply this algorithm. Although, again, here we can describe this algorithm for any integer valued function, but we want something special to happen if we start with a G parking function. Okay, so I kind of wrote what's going to happen in general, but our input is going to be this tuple. So let me explain what these are. So f is our function. S is one of those edge subsets. And I notice I missed something. U is a subset of the vertices, and then X is a subset of the edges. And then alpha and beta are going to be non-negative integers. And so here I forgot to add one more thing to the initialization, but you start with U contains Q, X is empty, alpha and beta are both 0, and then you start with S is just all edges in G. Okay. And so this diagram, what it's doing is it's describing all possible updates we could tuple. So let me explain what this means. So this first update, which I called A, what it's happening is we end up adding something to U, and then we end up adding something to X. So what I mean by this is, let's say this is my T, this is my edge E, and then I'm just calling this E sub H to represent this vertex that's now going to be added to U. So this is going to happen if the value of your function at E sub H is equal to 0, and E is not a bridge of S. So again, if you have your edge subset, you can always just think of it as the subgraph on that set of edges. So if E is not a bridge of that subgraph and the value at your vertex is 0, then you update the tuple in this manner. Just add the edge to X, the vertex to U, and everything else stays the same. Right. So the second case is similar to the first. The only difference is that we're adding 1 to alpha, and that's going to happen if E is a bridge. Okay. So that word should say bridge. I'm sorry, it's very messy. So in that case, we increase alpha by 1. The next case, so this is going to, so here's, sorry, I'm trying to think of the best way to draw this picture. I had done it. All right, so this next case is if E happens to be a loop. So E, a loop. So what we do is we then want to remove E from our edge subset, and then we want to add 1 to beta, and then everything else stays the same. And then the last case, so maybe actually that's the last case is if we try to grow an edge between edges that are already in T. So in particular, what I'm writing as T is just the graph on U and X. Okay, so if we have this situation, we get rid of E, and then everything else stays the same. So the algorithm is going to terminate when something I call T sub F. So again, it's going to be whatever U and X we have at this time, whenever this tree spans the connected component of S, which contains your root Q. So in other words, something that might happen is either you're going to end up getting a tree which spans all of your graph, or you might end up disconnecting your graph at some point. And so T sub F would just be span the connected component containing Q. So I'm going to go ahead and go to the next slide. That's okay. So basically these options of how to update our tuple. And if you have some familiarity, with things like Dar's algorithm or any of these algorithms which produce the bijections we have in mind, you might have an idea of why we are doing the updates in this way. So some standard things that we can prove about this algorithm, and they're pretty easy statements because you can find very similar statements in almost any paper about any of these bijections. But we do want to show that the algorithm will terminate on a spanning tree of your graph if and only if f is a G parking function. And then we also want to prove that this algorithm produces a monomial in the M sub G. So by this, I mean, we're going to define, and I wrote it down here, is that we're going to define a map from our parking function, G parking functions, to our monomials based on the assignments, and this shouldn't say rho, this should say F, that F is sent to the monomial X to the alpha, Y to the beta, where this alpha and beta are the integers from our algorithm. And then tau, this is from parking functions to spanning trees, and this is just our assignments of F to your terminating tree T sub F, which again should be spanning if and only if you have a G parking function. All right. So what we also want, and let me just a minute, because I don't want to erase what I have up. Okay, I think for now I'm good. So what we've done is we've taken this tree growing sequence, we've applied an algorithm, which, if you believe me, you can, I'm not going to go through the proof, but it's going to take each parking function, assign a spanning tree, and it's also going to assign a monomial that shows up in the top polynomial of G. So I want to do a slight change in perspective, because when defining the algorithm, I was just thinking about taking one function at a time. instead, I now want to think about taking the entire set of parking functions. And what I want to do is I want to apply this algorithm, but I want to think of applying it to all parking functions at once and perform what I call splitting operations with respect to the deletion contraction principle. So I have some notes because I need to add something. Yeah, so I want to add something to this. So what I mean by these splitting operations. So what I want to do is I want to split when applying the TGS algorithm, when we're given some tree growing sequence, according to whether at each step whether the edge E and that's next in question is added to X, our edge subset, and adding to X is an analogy with contraction of the edge, or deleted from S. Okay, so that's how that's what I mean by splitting. And then I just stated here, this is a very purposeful analogy with the Tut recursion formula, which tells us how to compute the Tut polynomial recursively based on whether our edge is where basically you're deleting and contracting each edge at a time. Okay. So 2 observations, and this is really what they're important observations. They're not too difficult to write down. You just have to write down the definitions. But if you think of the set of G parking functions, and so let me just choose. I should preface it. Choose some edge E. So the set of G parking functions, and maybe E is, I'll just call it E sub H, E sub T. So I should actually draw a picture. So for example, if we just start, maybe our edge, this is my edge E, so that I'm thinking about E sub H. So the set of parking functions where the value at E sub H is 0 is in one-to-one correspondence with the parking functions of the contraction of G at E. Unless, so there's just one thing. So if E is a bridge, then we actually get the correspondence is actually between all parking functions of G. So that's that's a special case. And then the set of parking functions where the value at E sub H is greater than or equal to 1 is in bijection with parking functions of the graph G minus E. So, and then again, we have a special case that if E is a loop, then this is actually equal to our original set of G parking functions. So so what we can think is if we we have a tree growing sequence, we always start at our root vertex Q, and as we apply the algorithm and we start growing our tree, we split the set of G parking functions according to this, in this manner. So if E is added to X, we contract it. If E is deleted, sorry, if E is added to X, whether E is added to X or E is deleted. And that's how we split the set of parking functions. And then we do this at each step of the algorithm. So these observations, really their purpose is just to say that this splitting, we don't lose any parking functions during this splitting. Since, again, adding to X corresponds to contracting the edge, and then we have deleting the edge. So I have this bigger diagram that is, its purpose is to try and explain visually what's sort of happening. So here I just have like, I have the maps sigma sub g. So, and then we start with the entire set of parking functions. And we have two options. We either are contracting E, adding it to X, or deleting E. If we contract E, we actually stay, because according to the algorithm, we don't do anything with the edge E. We add the edge E to X, but we don't do anything. It still stays in, we stay in the same edge subset, I guess. So this might be, it might be easier if I write it this way. So if you add an edge to X, we still apply sigma sub S again. But if you delete the edge in question, then you next consider the map sigma of S minus E. So that's what this diagram on top is depicting, just our options between staying in the same edge subset or moving on to an edge subset after deleting an edge. And down here is showing what's happening with our set of G parking functions. And then we have the special cases here if E is a loop. And then, sorry, I did that backwards. So special cases here if E is a bridge, and then here if E is a loop. So those are our special cases. And then like the E primes on both sides are not necessarily the same edge. I just forgot to name them something differently. So we just get this, like, as we split the set of G parking functions, what ends up happening is we're just forced to get one-to-one correspondences between the parking functions, the spanning trees, and the monomials.
Just to interrupt quickly, as a time check, it is almost 2 o'clock. So if anyone has to be anywhere, feel free for that. You can go a little longer if you want to. Like, we don't have a super official amount of time, but if somebody has something that they need to do, that's.
I always talk way longer. I prepare for way more than I know I will have time for. But the idea is, when we take this perspective of taking the set of G parking functions and splitting them as we apply the algorithm, this is how we can show that the maps, if I go back up, this is how we can show that these two maps, rho and tau, are going to be bijective correspondences, because we don't lose we don't, the sets are all these sets are the same size. So that's kind of like a classical I keep calling it the same thing. So this is tau, this is rho. Sort of classical facts that all three of these sets are the same size. So with the splitting, it's just a way to prove that these are one-to-one correspondences, and furthermore, they're onto, so they end up being bijective correspondences. Okay. So I'm not going to have time. I don't think I'll be able to go into detail with this. And I was going to like draw on this slide just a reminder of Dar's burning algorithm. But one thing I've done is I've taken this tree growing sequence algorithm and I've fit a few fit a few bijections from the literature into the context of a tree growing sequence. And one of those is Dar's algorithm. It's like probably the easiest one that one can think of to do this with. But the idea is that Dar's burning algorithm, there are many versions, but one version is you have a total edge order on your graph, and your edge order is what determines your bijection between parking functions and spanning trees. So here, this is just supposed to, this just means set of edge orders. This is the set of tree growing or collection rather, maybe, yeah, collection of tree growing sequences. And this just means these bijections tau between the set of parking functions and the set of spanning trees. And these are our bijections rho. So what you can do is you can just define, yeah, and there's only one map. You can just define a map that takes an edge order, and from that edge order defines a tree growing sequence algorithm. Or sorry, not an algorithm, it defines a tree growing sequence. So it tells you what data you want for your maps. It tells you the data of your maps. So in doing so, you can do it in such a way that the bijection you get between parking functions and spanning trees or tut monomials is the same bijection you get by running Dar's algorithm with this same global edge order. So kind of like the proposition is just that these diagrams commute. So D is just representing take a global edge order, run Dar's algorithm. I guess it should stand for Dar. Run Dar's algorithm, you get this bijection. And here's our bijection that we get from the tree growing sequence algorithm. And we happen to also get, so maybe should be that they commute. And we actually happen to get a commutative diagram if we run Dar's algorithm with this global edge order, and then we think of the bijection between spanning trees and monomials based on internal and external activities. So that's something I don't want to take too much time to explain it, but this is just fitting classical algorithms into the context of the tree growing sequence algorithms. So some other bijections are a family of bijections by Chebykin and Pilievsky. I think it's like it's from 2008, so quite a while ago. But they define bijections based on what are called based on proper sets of tree orders. So it's a way to take every tree, so you choose a root, and it's a way to take every rooted tree, not necessarily spanning, just every rooted tree, put an order on the vertices in your tree, and there has to be compatibility between those orders. And the compatibility I wrote down here according to these bullet points, but an example of how to obtain a proper set of tree orders. I wrote it out on a different piece of paper, so I just want to make sure. Okay, so let's say this is my graph, and I choose this to be my root, and then I do want some sort of global vertex order. So I call them V1, V2, V3, and then the subscript will say, kind of determines the order. So one way to get a proper set of tree orders is you could take every spanning tree, I guess there are 8 of them, I won't write all of them out. And the root always is given the order 0, and then you order the rest of the vertices by, for example, you could run a breadth first search, and you can order the vertices according to when you add them in that search. You could also do the depth first search and order them according to that algorithm, or you can do like a more greedy type of algorithm and then order vertices according to that algorithm. So there are ways. So if I was just greedy, I guess I should finish the example. If I was just greedy and I didn't label my root correctly, sorry, that's not my root. This is my root. So if I were greedy, I would say 1, 2, 3. On this one, if I were greedy, I would go 1, 2, 3, and so on. So there are ways to obtain a proper set of tree orders. And then let me just explain. So what they do is, for every proper set of tree orders, they define a bijection between parking functions and spanning trees. They also have an inverse bijection, which they describe. And I won't describe it in detail, but they define this bijection. And so what I wanted to do is define a map between the collection of proper sets of tree orders to the collection of tree growing sequences. And if you define it the right way, I mean, you could probably define it in a lot of ways, but if you define it the right way, then omega will end up being injective, meaning, well, we all know what is meant by injectivity, but omega will end up being injective. And furthermore, we will have that this diagram is going to commute for any choice of set of tree orders. So that was a little trickier to prove, because their bijection, what the algorithm does, so maybe I will kind of draw. So here they have some tree that they've already grown, and to grow the next tree, they consider vertices, neighboring vertices that have like a certain number of edges. So let's say our function has value 2 here, let's say it has value 3 here and value 0 here, then they only consider the vertices that have at least one more edge to the previous tree than the value at the vertex. So we could consider this vertex and this vertex, but not that one. So the difficulty with defining this map is because they end up like kind of skipping some edges. So they end up not considering all neighbors. So the point is, it was just hard for me to do this part. But we're fitting this family of bijections into the context of tree growing sequences and showing that we can just get out the same correspondence between parking functions and spanning trees. All right, and then I have an example, but I won't go through that. And then sort of the last algorithm, or the last bijection I came across that I considered is one by Chang, Ma, and Ye, and they have a paper where their bijection, supposedly their bijection between parking functions and monomials bypasses spanning trees. And the motivation behind that is they wanted to be able to write the Tup polynomial as a sum over the parking functions. And their construction is based on what's called a process order. And if you're figuring out a process order on your vertices, process order is an order on your vertices. It's achieved in a very similar way to Dar's algorithm. But what I think that there is a tree growing sequence which can describe their algorithm. And if so, then you kind of automatically pick up can pick up a spanning tree along the way, because if you apply the TGS algorithm, you're going to get out both a spanning tree and a monomial. So I have an idea of like how to get the same bijection between parking functions and monomials, and then we also get a spanning tree. I just haven't, this is difficult for me, at least. All right, so that's really all that I have more, but that's sort of like the first part, I would call it, of this work, is simply defining the tree growing sequence and its algorithm and comparing it to algorithms which are already known, and being able to fit and generalize in a way the algorithms which we already know. So I don't think there are very many people here still, I'm guessing, but I'll stop here if there are questions, or if anyone wants to stay, I can talk about zonotopes for a little bit.
All right, thanks, Carrie. Good.
Thank you.
Action along with lateral cropping. So does anyone have any questions?
Yeah, I was curious. So at the beginning, maybe you said this and I missed it, but at the beginning you talked a little about the connection between these G parking functions and chip firing.
Yeah.
Is there anything your algorithm can say about like the Picard group or something like that? Is there a way to phrase this?
Oh, for the algorithm? I haven't really thought about that yet. I have thought about, like, let me go down a few slides.
Oh, you're prepared. Oh, great.
So I have thought about like the tree growing sequence and its relation to like the Abel-Jacobi map, discrete Abel-Jacobi map. So I have thought about the Picard group for this, but I don't have an answer to that, I guess. Oh, that's a good question. Something for me to think about. Sort of like the last big question, like this was one of my last slides, is taking this triangle and just adding one of those other objects that was in the original K6 diagram. And these are tiles of a certain zonotope. So when I think about that more, then I will definitely be thinking more about the Picard group.
And actually, remind me, in this picture, is M sub G, are those, that's not the graphic matroid associated to G, is it? Or
no, that's the set of monomials. So I guess multi-set, I should have said that. So if you have your Tut polynomial, just take every monomial, and those are the elements of your multi-set.
the terms of your Tut polynomial?
Yeah.
Yeah.
So I think one way to connect to the Picard group, could you just literally take the parking functions, and those are in a very natural bijection with the Picard group?
Yeah, they are. Yeah.
So I think that could work.
Because like if you think of them, the G parking functions as Q-reduced divisors, then you have a unique one of those in each equivalence class of, each equivalence class, I think, of divisors, and then you can do some sort of like translation so that you get something of degree 0. Anyways, yes, I know how it works. I always like forget how to explain it. I have it in front of me.
I think one way is if you just since you don't consider putting anything on Q, right?
Yeah, I'm not. So in that way you can think of it as an effective divisor.
Yeah.
And you subtract.
But if you put negative the sum of the remaining chips on Q, then that
Yeah.
gives you a natural way to get an element of the Picard group.
Yeah, that's exactly right. Yeah, because you'll start with something that's technically effective, and then subtract and get something. Yeah, so there I don't think it would be too much of a stretch to go back to the tree growing sequence algorithm and think about the Picard group. But I have thought of it in the context of isonotopal tilings, which is the end of this, but I don't know if there are any other questions, or I don't know if anyone wants to stay and I can sort of like finish my talk, or I guess technically this wouldn't be just a one-day talk because I've gone so long.
Maybe it's time to stop the recording. That's usually what we do at this stage.
Yeah,
And then,
well, first we'll
yeah.
thank the speaker again, and then we can stop
Okay.
the recording. So thank you.
Oh yeah, you're welcome. Thank you.